Good morning. Myself, Srinivas Reddy, Assistant Professor of Mathematics, Government Degree College, Janagam. Today we have to discuss about uh, discontinuity and properties, types of discontinuities, and some problems on discontinuity, and some example problems. Let's go. Begin the class. What is discontinuity? A discontinuity means a function which is not continuous is called a discontinuity. A function which is not continuous is called a discontinuity. Therefore, Therefore, a function is said to be discontinuous at a point of its domain if it is not continuous at that point. It is not continuous at that point. Therefore, the discontinuity can be arranged in two cases. Number one is limit x goes to c f of x is exists, but it is different from the value f of c. That means at the function value is different from the limit value. In that case, the function is said to be given function is said to be discontinued at that point, and the limit does not exist. If limit if does not exist, then at that point, therefore it is called a discontinuity at that point. There are three types of discontinuities. One is removable discontinuity, and second one is jump discontinuity or discontinuity of first kind, and third one is discontinuity of second kind. What is removable discontinuity? Removable discontinuity is limit x goes to c f of x exists, but it is not equal to f of c. That means the limit values existed, left limit and right limit and left limit are exist and both are equal, but which is different from function value at x equal to c. Then f is said to be a removable discontinuity at x equal to c. Such discontinuity can be removed by assigning a suitable value at the function value at x equal to c. What is first kind discontinuity or jump discontinuity? A function is said to have a discontinuity of the first kind at x equal to c if limit x goes to left hand limit. This is called right hand limit. The right hand limit x goes to c plus f of x and limit x goes to c minus f of x both exist but are not equal. That means LHL is not equal to left hand limit is not equal to RHL. Both are existed L1 and L2, but L1 is not equal to L2. Then this discontinuity is called a jump discontinuity. Discontinuity of second kind. A function f is said to have a discontinuity of second kind at x equal to c if neither right hand limit or nor left hand limit are existed. That means left hand limit does not exist, and that means converges to r plus or minus infinity, and right hand limit are also does not exist, converges to plus or minus infinity. In these cases, the discontinuity is called a discontinuity of second kind. Problem 1. Check the continuity at x equal to 1 for the function f of x equal to x square minus 1 by x minus 1 for x not equal to 1 and equal to 1 for x equal to 1. Okay, given that, first of all, find the limit value. Limit x goes to 1 f of x is equal to limit x goes to 1 x goes to 1 x square minus 1 by x plus 1, sorry, x minus 1. This value can be written as limit x goes to 1 x square minus 1 can be a square minus b square equal to a minus b into a plus b all divided by x minus 1. X minus 1 are cancels. Therefore, limit x goes to 1 into x plus 1. This value equal to 1 plus 1 is equal to 2. Therefore, the limit value limit x goes to 1 f of x is equal to 2, but which is not equal to the function value at f of 1. But we know that f of 1 equal to 1. Therefore, the limit existed and which is not equal to function value. Therefore, at x is equal to 1, f has removable discontinuity. Removable discontinuity. If we define f of 1 equal to 2, f of 1 is equal to 2, then this discontinuity equal to continuous. Therefore, this is called a removable discontinuity. Check the continuity at x equals 0 for the function f of x equal to e power 1 by x minus e power minus 1 by x by e power 1 by x plus e power minus 1 by x for x not equal to 0 equal to 1 for x equal to 0. Solution. First of all, find the left hand limit. LHL implies that limit x goes to 0 minus f of x. But we know that limit x goes to 0 minus f of x is equal to limit h goes to 0, limit h goes to 0, f of 0 minus h. That means limit x goes to a minus left hand limit equal f of x is equal to limit h goes to 0, f of a minus h, f of a minus h. Similarly, the right hand limit equal to limit x goes to a plus f of x is equal to limit h goes to 0, limit h goes to 0, f of a plus h. These are two formulas for left hand limit and right hand limit. Therefore, this implies that if substitute x equal to minus h here, therefore limit h goes to 0, e power minus 1 by h plus e power minus minus cancels, e power 1 by h all divided by minus by e power minus 1 by h plus e power 1 by h. Therefore, this value equal to limit h goes to 0, limit h goes to 0. Take e power 1 by h common, e power minus 1 by h by e power 1 by h, 1 by e power 1 by h equal to e power minus 1 by h. Therefore, e power minus 2 by h minus 1 all divided by e power 1 by h into e power minus 2 by h plus 1. And this one cancels. If h goes to 0, then implies that 1 by h goes to infinity. Therefore, 1 by h goes to infinity, therefore e power minus infinity goes to, therefore e power minus infinity goes to 0. Therefore, this value equal to e power minus infinity minus 1 by e power minus infinity plus 1 equal to 0 minus 1 by 0 plus 1 equal to minus 1, which is left hand limit. What is right hand limit? The right hand limit of this one equal to limit x goes to 0 plus, limit x goes to 0 plus f of x is equal to limit h goes to 0, f of 0 plus h is nothing but f of h equal to limit h goes to 0, e power 1 by h minus e power minus 1 by h all divided by e power 1 by h minus e power minus 1 by h. Take e power 1 by h common, therefore limit h goes to 0. Since if we apply limit for this function, therefore e power 1 by h equal e power infinity by e power infinity undefined. Therefore take e power 1 by h common, therefore this value equal to 1 minus e power minus 2 by h all divided by e power 1 by h into 1 minus e power minus 2 by h. Therefore, e power 1 by h, e power 1 by h cancels. Now apply the limit value. Therefore, 1 minus e power h goes to 0, then 1 by h goes to infinity. Therefore, this is minus symbol. Therefore, this is converges to minus infinity. Therefore, e power minus infinity equal to 0. Therefore, 1 minus 0 by 1 plus 0, this value equal to 1. Therefore, left hand limit and right hand limit are existed. Therefore, left hand limit equal to 1 and which is not equal to minus 1 equal to right hand limit. Therefore, at x is equal to 0, at x equal to 0, but we know that what is the function value? Function value equal to, at x equal to 0, f of x equal to 1. Therefore, f of 0 equal to 1. Therefore, at x equal to 1, this has a first kind discontinuity or jump discontinuity. Therefore, at x equal to 0, f has a jump discontinuity. jump discontinuity from the left. Since the right hand limit equal to 1, this is minus 1, this is plus 1, which is equal to f of 0. Therefore, from right hand limit this is continuous, from left side this is not continuous. Therefore, this is called a jump discontinuity from the left. Jump discontinuity from the left. Next problem. Consider the function f defined by f of x equal to x minus 1 cosecant 1 by x minus 1 for x not equal to 1 and equal to 1 for x equal to 1. Check the continuity at x equal to 1. Therefore, first of all, find out left hand limit. This value equal to limit h goes to 0, sorry, limit x goes to 1, f of x equal to f1 plus, sorry, 1 minus left hand limit. This value equal to limit h goes to 0, f of 1 minus h. Substitute x equal to 1 minus h in this equation. Therefore, limit h goes to 0, 1 by 1 minus h minus 1 into cosecant 1 by 1 minus h minus 1. 1 cancels. This value equal to limit h goes to 0, 1 by minus h into cosecant x equal to 1 by sin x. Therefore, whole divided by sine of minus 1 by h. Minus 1 by h. Therefore, but sine function is oscillates. Sine function is oscillates, but 1 by h is converges to minus infinity. Therefore, which is converges to minus infinity. Similarly, the right hand limit equal to limit x goes to 1 plus f of x equal to limit h goes to 0, f of 1 plus h. This implies that limit h goes to 0, 1 by 1 plus h plus 1 into cosecant x of cosecant of 1 by 1 plus h plus 1, sorry, minus 1, and this is also minus 1. Therefore, 1 cancels, and this value equal to limit h goes to 0, 1 by h into sine 1 by h, and which is converges to plus infinity. Therefore, the left hand limit and right hand limit does not exist. Therefore, this discontinuity is called, since the limit does not exist. Therefore, this discontinuity is called a second kind. It's called a second kind. Show that the function f on 0, 1 defined as f of x equal to 1 by 2 power n for 1 by 2 power n plus 1 less than or equal to x is less than 1 by 2 power n. For x equal to 0, f of 0 equal to 0 is discontinuous at 1 by 2, 1 by 2 square and 1 by 2. Therefore, given that the function value f of x equal to 1, substitute n equal 0 here. This value for 1 by 2 is less than, x is less than, this is only less than value, equal to 1 by 2 for 1 by 2 square is less than, x is less than 1 by 2, equal to 1 by 2 square for 1 by 2 cube is less than, x is less than 1 by 2 square. 1 by 2 square. Now check discontinuity at continuity at x equal to 1 by 2. Therefore, check the left hand limit at x equal to 1 by 2, x equal to 1 by 2 minus of f of x equal to, that means when x approaches from left side, that means x is less than 1 by 2. X is less than 1 by 2 takes here. Therefore, when x is less than 1 by 2, f of x equal to 1 by 2. Therefore, limit x goes to 1 by 2, f of x equal to 1 by 2. This value equal to 1 by 2. This is left hand limit. And what about right hand limit? Limit x goes to 1 by 2 plus f of x equal to limit x goes to 1 by 2 f of x. When x approaches from right side, that means x is greater than 1 by 2. When x is greater than 1 by 2, f takes this value, therefore this value equal to 1, therefore this is equal to 1. This is RHL. Therefore the left hand limit and right hand limit are existed and which are not equal. Therefore the limit of the function does not exist. Therefore at x is equal to 1 by 2, f has a discontinuity, and which is also called a first kind discontinuity. X equal to 1 by 2, f of x has discontinuity. Similarly, we can check at x equal to 1 by 2 power n. At x equal to 1 by 2 power n. Therefore, limit x goes to 1 by 2 power n minus 1 by 2 power n minus f of x equal to limit x goes to 1 by 2 power n. F of x can take as 1 by 2 power n. This equal to 1 by 2 power n. Similarly, limit x goes to 1 by 2 power n plus right side. Therefore, f of x equal to limit x goes to 1 by 2 power n. This value equal to 1 by 2 power n minus 1. 1 by 2 power n minus 1. That means when x is greater than 1 by 2 power n. Therefore, this value equal to 1 by 2 power n minus 1 equal to 1 by 2 power n minus 1. Both are not equal. Therefore, at x is equal to 1 by 2 power n, f has a discontinuity. Therefore, for all n equal to 0, 1, 2, 3, 4 dash. Therefore, at x is equal to 1 by 2, 1 by 2 square, 1 by 2 cube, up to so on. F is x at x equal to 1 by 2, 1 by 2 square, 1 by 2 cube, dash dash at up to 1 by 2 power n. Then f has a discontinuous at these points. Therefore, hence proved. Next problem. Determine the constant a and b so that the function is continuous everywhere. Given that we have to find that the function is continuous everywhere. But we know that automatically when x is less than or equal to the function value is taken, this is a polynomial function. Every polynomial function is continuous everywhere. Therefore, when x is less than or equal to 1, when x is less than 1, the given function is continuous. And when x is greater than 3, this is also a polynomial function. Therefore, this is also a continuous. But in between these two, if we check at x equal to 1 and x equal to 3, if it is continuous at x equal to 1 and x equal to 3, then the total function f of x is continuous everywhere. Therefore, we have to check continuity at x equal to 1 and 3 only. Therefore, check the continuity at x equal to 1 and x equal to 3. At x equal to 1, the left hand limit, therefore limit x goes to 1 minus f of x equal to limit x goes to 1. When x approaches to 1 from left side, that means when x is less than 1, the function value, when x is less than or equal to 1, the function value takes 2x plus 1. Therefore, this value equal to 2x plus 1 equal to 2 into, now apply the limit value, 2 into 1 plus 1 equal to 3. Similarly, the right hand limit, when x approaches to 1 plus, that means when x is greater than 1, the function value equal to ax square plus b. Therefore, this value equal into f of x equal to limit x goes to 1, ax square plus b. Now apply the limit value, this value equal to a into 1 square plus b equal to a plus b. Given that the function is continuous everywhere, that means at each and every point of the domain real number system, f is continuous. Therefore, at x equal to 1, given that the function is continuous, therefore at x equal to 1, given function is continuous. Therefore, this implies that the left hand limit equal to right hand limit equal to function value. but we know that at x equal to 1 takes here, therefore at x equal to 1 f of x equal to 2 into 1 plus 1 equal to 3, therefore LHL equal to 3, RHL equal to a plus b, and also equal to f of 1 is also equal to 3. That means a plus b is equal to 3, which is equation number 1. Next, to check continuity at x equal to 3, therefore at x equal to 3, limit x goes to 3 minus f of x equal to limit x goes to 3 f of x when x is less than 3, f of x takes ax square plus b, therefore this value equal to ax square plus b equal to 3a square, a into 3 square is 9a plus b, 9a plus b. When x approaches from right, that means 3 plus f of x equal to limit x goes to 3, when x is greater than 3, f of x equal to 5x plus 2a, this value equal to, now apply x equal to 3, therefore 5 into 3 equal to 15 plus 2a. Therefore given function is continuous, therefore at x equal to 3 f is continuous, therefore the left hand limit equal to right hand limit. This implies that 9a plus b is equal to 15 plus 2a. Take left side a, therefore 7a plus b equal to 15. This is equation number 2. Solve these two equations. 1 minus 2 or 2 minus 1. 2 minus 1 implies that b cancels. 6a is equal to 15 minus 3 equal to 12. This implies that a is equal to 2. Now substitute a is equal to 2 here. This implies that b is equal to 1. Therefore a is equal to 2 and b is equal to 1. Therefore at a is equal to 2, b is equal to 1, the given function is continuous everywhere. Next problem, show that the function f of x equal to mod x plus mod of x minus 1 is continuous at x equal to 0 and x equal to 1. Given that, but we know that mod x equal to plus x when x is greater than 0, equal to minus x when x is less than 0. Similarly, mod of x minus 1 equal to minus of x minus 1 if x is less than 0, and equal to 0 is less than x is less than 1. Similarly, when x is less than 1, this value equal to this one, and when x is greater than 1, this value equal to x minus 1. Therefore the function value, first of all find the function values. Equal to, when x is less than 0, mod x equal to minus x. Similarly, when x is less than 1, 0 is also less than 1. Therefore when x is less than 1, mod of x minus 1 equal to minus of x minus 1. Therefore minus of x minus 1 equal to minus 2x plus 1. If x is less than 0. Similarly, if 0 is less than x is less than 1. Therefore the function value f of x equal to, when x is greater than 0, mod x equal to x minus of x minus 1. Therefore this value equal to x cancels, only 1. Therefore when 0 is less than x is less than 1, and also equal. This is also true for equal values also. Therefore when x is greater than 1, f of x equal to, when x is greater than 1 means also greater than 0, 1 is also greater than 1, therefore x is greater than 0, mod x equal to x plus x minus 1 equal, mod x minus 1 equal to x minus 1, this value equal to 2x minus 1. Therefore Therefore the function values f of x equal to 1 minus 2x 1 minus 2x if x is less than 0, equal to 1 if 0 is less than or equal to x is less than or equal to 1, and equal to 2x minus 1 if x is greater than 1. Okay, now check the continuity at x equal to 0 and x equal to 1. Therefore the left hand at x equal to 0, LHL equal to limit x goes to 0 minus f of x. This value equal to limit x goes to 0. When x approaches to 0 from left side, that means x is less than 0. Therefore when x is less than 0, the function value equal to 1 minus 2x. Therefore 1 minus 2x. Now substitute limit value. Therefore 1 minus 2 into 0 equal to 0. This value equal to 1. What about RHS? The right hand limit equal to limit x goes to 0 plus f of x is equal to limit x goes to 0 when x approaches to 0 from right, that means x is greater than 0. When x is greater than 0, f of x equal to 1. Therefore this value equal to 1, this total value equal to 1. At x equal to 0 takes here, therefore at x equal to 0, f of 0 is equal to 1. Therefore left hand limit equal to 1 and right hand limit equal to 1, and also function value f of 0 is also equal to 1. Therefore LHL equal to RHL equal to f of 0. Therefore limit x goes to 0, f of x equal to f of 0. Therefore at x equal to 0, given function is continuous. Similarly we can check at x equal to 1. Therefore limit x goes to 1 minus f of x equal to when x is less than 1, f of x takes 1. Therefore this limit value equal to 1. This is LHL. Similarly, when x approaches from right, 1 plus f of x equal to limit x goes to 1 plus 1. When x is greater than 1, f of x equal to 2x minus 1 equal to 2 into 1, 2 into 1 minus 1 equal to 1. Therefore, at x equal to 1, f of 1 equal to 1. Therefore, left hand limit equal to right hand limit equal to f of 1. This is also equal to f of 1. This total value equal to 1. Therefore, the given function is continuous at x equal to 1 also. Therefore, given function is continuous at x equal to 0 and 1. Hence proved. Show that the function f is continuous at x equal to 0. Where we can do that? Given function is continuous at x equal to 0. We have to prove that given function is continuous at x equal to 0. First of all, find the left limit. This implies that limit x goes to 0 minus f of x equal to limit x goes to 0 minus is nothing but limit h goes to 0, f of 0 minus h equal to limit h goes to 0. Substitute x equal to minus h. Therefore, minus h into e power minus 1 by h minus e power 1 by h all divided by e power minus 1 by h plus e power 1 by h. Therefore, this value equal to limit h goes to 0 minus h into take e power 1 by h common into e power 1 by h into e power minus 2 by h plus 1 all divided by e power 1 by h into e power minus 2 by h. This is minus 1 and this is plus 1. Therefore, e power 1 by h cancel. Now apply the limit value. This value equal to 0 into 0 minus 1 by 0 plus 1. Therefore, 0 into minus 1 equal to 0. What about right hand limit? The right hand limit equal to limit x goes to 0 plus f of x is equal to limit h goes to 0, f of 0 plus h is nothing but f of h. Substitute x equal to h, this value equal to limit h goes to 0, h into e power 1 by h minus e power minus 1 by h whole divided by e power 1 by h plus e power minus 1 by h. Now take e power 1 by h common, therefore limit h goes to 0, h into e power 1 by h into 1 minus e power minus 2 by h whole divided by e power 1 by h into 1 plus e power minus 2 by h. E power 1 by h, e power 1 by h cancels. Therefore, this value equal to, now apply the limit value, therefore 0 into 1 minus 0 by 1 plus 0 equal to 0 into 1 equal to 0. But we know that the function value at x equal to 0 is also equal to 1. Sorry, this is 0. This is 0. Therefore, the function value at x equal to 0 is, therefore the left hand limit equal to right hand limit, which is also equal to 0. 0 is nothing but the function value. Therefore limit x goes to 0, f of x equal to f of 0. Therefore, at x equal to 0, given function is continuous. Is continuous. Next problem. Let f be a continuous function at x naught, then prove that mod f is also a continuous at x equal to x naught. If f is any continuous function, then mod f is also continuous. Okay, then here to prove that mod f is continuous at x naught, to prove mod f is continuous at x naught, at x equal to x naught, then we need to prove that limit of mod f of xn is converges to mod f of x naught for any sequence xn in the domain is converges to x naught. Okay, given that f is continuous, right? This implies that by definition, given that f is continuous at x naught, therefore for any sequence xn converges to x naught, implies that f of xn, limit of f of xn is converges to f of x naught, right? Therefore, by definition, limit f of xn converges to f of x naught means for any given epsilon greater than 0, there exists a natural number N is such that mod f of xn minus f of x naught is less than epsilon for all n is greater than or equal to N. Now assume that this is equation number 1. But we know that mod a minus mod b, but we know the fact that mod a minus mod b is always less than or equal to mod a minus mod of a minus b. By using this fact that mod of f of xn minus mod f of x naught of mod, which is always less than or equal to mod of f of xn minus f of x naught. Therefore, for n is greater than or equal to N, this implies that this value equal to mod of f of xn minus mod of f of x naught whole mod, which is always less than mod of f of xn minus f of x naught when n is greater than or equal to n, and this value equal to is less than epsilon, therefore which is less than epsilon. This implies that for any n greater than or equal to n, modulus of f of xn minus mod of f of x naught whole mod is always less than epsilon. Therefore, by convergence of which means that limit n goes to infinity, mod of f of xn is converges to mod of f of x naught. Mod of f of x naught. That means, therefore, for any sequence xn converges to x naught implies that for any sequence xn in a domain of given function xn converges to x naught, then we know that mod of f of xn is converges to mod of f of x naught. Therefore, by definition of continuous function, therefore mod f is also continuous. Therefore, f is continuous implies that mod f is also continuous. Mod f is also continuous. But the converse part of this theorem is not true. But the converse of above theorem is not true. That means if mod f is continuous, that means if mod f is continuous implies that f is need not continuous. For an example, f of x equal to 1 for f of x equal to for x is belongs to rational numbers, for all x belongs to rational number, equal to minus 1 for x belongs to does not belongs to x is, that means x is does not belongs to q means x is belongs to every rational number. But we know that this is not continuous everywhere, but we know that mod f equal to 1 for all x belongs to R, R whole real number system. But we know that R equal to set of all rational numbers union q dash. Q dash is nothing but set of all irrational numbers, this one. Therefore, mod f equal to 1 for all x belongs to R. Therefore, mod f is a constant function. Every constant function is a continuous function. Therefore, mod f is continuous, but f of x is nowhere continuous. Thank you very much.